Good morning. Welcome to Currents World. In this video, let us discuss NERNST distribution law and its deviations. What are their applications? Okay. There are two deviations or modifications of NERNST distribution law. They are one, association of the solute in one of the solvents. The solute undergoes association. For example, benzoic acid in benzene layer undergoes dimer formation. So the NERNST distribution ratio K equal to C1 by nth root of C2. Okay, where C1 is the concentration of solute in the phase 1 and C2 is the concentration of solute in the phase 2. Okay, for dimer, let us put n equal to 2. For dimer, n equal to 2, therefore C1 by square root of C2. For n equal to 3, for solute undergoing trimer, then C1 by cube root of C2. Okay, if it undergoes n, then nth root of C2. The second case is dissociation of the solute in one of the solvents. In this case, K equal to C1 by C2 1 minus alpha, where alpha is the degree of dissociation. It is the fraction of the solute dissociated. Therefore, it is the NERNST distribution law is applicable for solute in unassociated or undissociated form only. Therefore, C1 is the concentration of the solute in phase 1 and C2 1 minus alpha is the concentration of solute in phase 2. Okay, let us discuss and derive the equation association of the solute in one of the solvents. Okay, let solute molecules are associated or undergoes association to give NHA reversible arrow HA n times, where HA is the solute which undergoes association. For example, benzoic acid 2 times gives dimer. It will be associated to give dimer in phase 2, whereas in benzene layer, in water layer, it is C1. Okay. The associated molecules will exist in equilibrium with the unassociated molecule. The associated molecules will be in equilibrium with the unassociated molecules. Okay, let C1 be the concentration of the solute HA in phase 1 and C2 is the total concentration of HA in phase 2. Okay, let us apply the chemical equilibrium to obtain the K value. Okay, let us write in reverse direction. It is nothing, equilibrium only. HAN gives reversible arrow NHA. Therefore, by applying law of chemical equilibrium, the equilibrium constant is equal to HA to the power n, concentration of HA to the power n divided by concentration HAN. Okay, subscript n. HA superscript n, okay, cross multiply. So, K into concentration of HA subscript n. Then, okay, let us take nth root. Okay, so here concentration of HA nth root. Okay, this one. Next, as in benzene layer, benzoic acid is fully associated, mostly associated. Therefore, as HA largely associated in phase 2, then C2 equal to this only, not this. Therefore, C2 equal to HA, concentration of HA, dimer, concentration of the dimer only, C2 equal to. Okay, so let us substitute in this expression C2, HA. Okay, So HA equal to nth root K, okay, HA, instead of HA you put, let us take K outside, K prime, so square root of nth root of C2. Now the distribution law is valid only for unassociated solute molecules, okay, unassociated, only the molecules in the same state in both the phases. Therefore K equal to C1 divided by concentration of HA in phase 2. Therefore HA equal to C1 divided by nth root of C2. For benzoic acid N equal to 2, therefore C1 by square root of C2. Okay, let us consider the second case where dissociation of the solute in one of the phase, one of the solvent. Let HA dissociates. Let HA dissociates in phase 2, but not in phase 1. Let C1 be the concentration of the solute HA in phase 1, and C2 is the total concentration in phase 2. The distribution law is only valid for the ratio of concentrations of similar species, not for this species. Similar HA. So undissociated. The distribution law is valid for the ratio of concentrations of undissociated similar molecular species in the two solvents. Then therefore HA is a weak acid. For example, acetic acid in aqueous solution, it undergoes dissociation, partial dissociation or ionization, where alpha is the degree of dissociation. It is the fraction of solute dissociated, therefore 1 minus alpha. We have taken C2, total concentration C2 in here, therefore C2 1 minus alpha, C2 alpha. K equal to concentration of HA in undissociated. This is undissociated, and this is the undissociated will be C2 1 minus alpha at the equilibrium. Therefore C1 by C2 1 minus alpha, where alpha is the degree of dissociation of the solute in phase 2. Okay, we can calculate, if we know C1, C2, K is a constant, then we can calculate the degree of dissociation, or if we know alpha, C1 and C2, then we can calculate the NERNST distribution coefficient. Thank you for watching. Please share and subscribe. Thank you very much.